Hey everyone, so glad you're joining us for another deep dive on the Explainer. Today, we're looking at a totally fascinating piece of engineering that works tirelessly behind the scenes to keep our modern world powered: transformer protection schemes. Right? If you've ever wondered how the massive transformers on our grid avoid tearing themselves apart when things go sideways, well, you're in exactly the right place. We're going to unpack the ingenious mechanisms that keep these critical assets safe.
But before we look at the solutions, I've got a bit of a mystery for you. Why do perfectly healthy transformers sometimes just trip their own breakers? Shutting down power when there's literally zero actual damage to the system. In our engineering story today, these false trips are the ultimate villain. They cause completely unnecessary blackouts, massive headaches for grid operators, and they cost a ton of time and money. So, how do we stop this villain while still protecting the transformer from real danger?
Okay, let's dive into this. Here is our roadmap for today. 1. Basics of differential protection. 2. The phase shift problem. 3. Fixing phase with inverse CTs. 4. Inrush currents versus faults. 5. The restraining coil solution. And finally, 6. Normal versus fault conditions.
All right, Section 1, Basics of Differential Protection.
You can think of differential protection kind of like a perfectly balanced electrical weighing scale. It compares two electrical quantities, specifically the incoming current entering the transformer's winding and the outgoing current leaving it. The golden rule here is incredibly simple. During normal, healthy operations, what goes in must exactly equal what comes out. If there's any difference, a differential, the relay detects it and instantly triggers a safety trip.
So under balanced current conditions, meaning normal running operation, the incoming and outgoing currents match perfectly. And because they match, zero current flows into what we call the relay's operating coil. But if an internal fault occurs, like a short circuit right inside the transformer's windings, that delicate balance is instantly shattered. You get unbalanced current. That difference flows directly into the operating coil, which acts as the trigger to trip the circuit breaker and ultimately save the transformer.
Section 2. The phase shift problem.
Now here's where things get tricky. The physical design of the transformer itself actually creates a major problem. In those massive grid transformers, we often use different winding configurations, like a star setup on one side and a delta setup on the other. Because of the way these are physically wound and connected together, a star-delta transformer naturally shifts the electrical phase. Depending on the exact configuration, this could be a shift of plus 30 degrees, minus 30 degrees, or even 45 degrees.
So, why does a simple angle shift matter? Well, because these phase shifts cause absolute chaos for our protection scheme. That natural phase shift artificially alters the magnitude of the current on either side of the transformer. Remember our perfectly balanced weighing scale? Yeah, the relay looks at these artificially changed currents and just gets completely confused. It sees a difference, falsely pushes that phantom difference right into the operating coil, and bam! Unwanted circuit breaker trip. A perfectly healthy transformer shuts down just because of its own geometry. Crazy, right?
Section 3. Fixing phase with inverse CTs. To measure all this electricity, we use current transformers, or CTs. And to perfectly compensate for that natural phase shift of the main transformer, engineers do something brilliant. They wire the CTs in the exact opposite or inverse configuration. So if the main transformer winding is connected in a star configuration, you absolutely require a delta-connected CT on that side. Conversely, if the transformer's outgoing side is delta, well, it requires a star-connected CT. These inverse CTs introduce an equal and opposite phase shift, perfectly canceling out those artificial differences. Problem solved. This fix is so crucial that if you're a grid technician out there troubleshooting a false trip, this is exactly what you look for. Step 1, check your main transformer configuration. Is it star-delta? Step 2, strictly verify your CT connections. Are they truly inverse? If they aren't, boom, you found your problem. Finally, step 3, you measure the operating coil current under normal load. If there's phantom current flowing while the system is totally healthy, your phase compensation is likely wrong.
Section 4, Inrush currents versus faults. Okay, so there are two main culprits when it comes to temporary current imbalances. First up is the magnetizing inrush current. When you first flip the switch and turn a massive transformer on, it gulps down a huge amount of current just to magnetize its core. The second culprit, tap-changing operations. When grid operators adjust the transformer's voltage by changing its turns ratio, the currents briefly become unmatched. Both of these events create temporary imbalances that mimic real faults, which threatens to falsely energize that operating coil we talked about.
Section 5. The restraining coil solution.
So, the crucial point here is understanding the distinct roles of two very different coils. On the left, we've got a new component, the restraining coil. Think of it as your gatekeeper, or a buffer. It's specifically designed to recognize and block those minor, temporary imbalances caused by inrush currents and tap changes. It quite literally restrains the system from acting rashly. Then on the right, we have the operating coil. This remains the ultimate trigger. It sits right behind the restraining coil, just waiting to trip the breaker, but only when a true fault actually occurs.
Section 6. Normal versus fault conditions. Tracing the current paths here makes the theory incredibly clear. Let's look at the normal operation condition. The incoming CT measures 2 amps and the outgoing CT measures 2 amps. Perfectly balanced, right? So 0 amps flow into the operating coil. But look at the bottom row, an internal fault. Let's say a short circuit happens inside the winding. Suddenly, the incoming CT spikes to 10 amps, while the outgoing is still only 2 amps. That massive 8 ampere difference has literally nowhere else to go but straight into the operating coil, instantly tripping the relay.
Now, wait a second. Earlier, we said the restraining coil blocks current. So why doesn't it just block those 8 amps? Well, in reality, a true internal short circuit doesn't just create an 8 amp difference. It violently spikes to hundreds or even thousands of amps, like the massive 1,000 amp figure we're talking about right here. This physical reality is the key to contrasting an actual fault against those minor magnetizing inrush currents. The coil distinguishes between them purely by the sheer overwhelming magnitude of a true fault.
During a catastrophic internal fault, that restraining coil still tries to do its job. It really tries to block the imbalance. But the sheer magnitude of a 1,000 amp true fault current is simply way too severe. It completely overpowers the restraining coil's buffer, surging right past it and flowing straight into the operating coil. And this guarantees the circuit breaker trips, safely isolating the transformer before it can be completely destroyed.
Which leaves us with this final thought. Without this incredibly delicate, hidden balance, inverse CTs perfectly canceling out physical phase shifts, and restraining coils intelligently buffering normal inrush while yielding to catastrophic faults, would our modern, complex power grid even be able to function? The answer is a resounding no. So, the next time you flip a light switch, remember the brilliant invisible differential protection acting as a silent guardian for the grid. Thank you so much for joining me on this explainer.